All right, so in this video, we're going to be breaking down the initial rates method, and this is a common way that we use to determine the rate law of a reaction given experimental data like this. So this is a very common problem you'll see in general chemistry or AP chemistry or whatever chemistry you're taking. This is a common thing you'll see. So if you're given a table like this with experimental data, you're going to have to be using this method. So basically what you're doing is if you're given this type of concentration and rates data, what you're going to want to do often is find the reaction orders with respect to each of the reactants and the overall order of the reaction, writing out the rate law, all those types of things are things you could be asked. So let's start off with the rate law itself. So the rate law is telling us how the rate of a reaction is dependent on the concentration of the reactants. So how is the rate, or how quickly the reaction proceeds, how is that going to vary if we change how much of each reactant we have? That is basically what the rate law is telling us. So there's a general form for this rate law, and that's going to be your rate is simply going to be equal to k, lowercase k, times the concentration of A to the m times concentration of B to the n, let's say. And so in this general form, what are we looking at exactly? The k here, this again, this is a lowercase k, which is very different from an uppercase k, which you'll see in other areas of chemistry. But this lowercase k here is going to be your rate constant. This is your rate constant. These letters M and N, well, you already know what A and B in square brackets are, right? We know that square brackets is short form for concentration. So if we write A in these square brackets, it's referring to the concentration of A, one of the reactants here, and B is the concentration of reactant B. And so what are these M and N? Well, M and N. Well, these are going to be the reaction orders with respect to each reactant. So M is the reaction order with respect to the reactant A, and N is the reaction order with respect to B. So these M and N, they are simply the reaction. RxN is short form for reaction orders. I don't know why this is glitching out. Okay, let's try this again. Reaction orders with respect to each reactant. Okay, and then let's say we want to find the overall order of the reaction. Let's just cover that while we're here. The overall order of the reaction is simply going to be equal to the order with respect to each of the reactants summed up. So that's just M plus N. So what you're going to want to do is just add the order of the reaction with respect to reactant A and that with reactant B. That is our M plus N, and this is going to give you your overall order of the reaction. Let's say that our value, the reaction is first order with respect to A and second order with respect to B. So that means our overall order is going to be 1 plus 2, giving us an overall reaction order of 3. So that's really all we're dealing with. Very simple. So as long as you get the orders with respect to each of the reactants, you can very easily find the overall order. And so what this initial rates method is doing is we're basically running several experiments here, right? Or oftentimes you may not be, running the experiment yourself. You'll be given this data on an exam, right? So you'll be given the data from several experiments here, and the one thing that you're changing here is the initial concentration. You're just changing the concentrations of the different reactants in these different experiments and seeing how that affects your rates, your initial rate specifically. The initial rate, as the name would suggest, is going to be the rate right after the reaction starts. And the reason we do this is because this kind of avoids complications that may occur from reverse reactions, which start to proceed as you continue later on in a reaction, or other changes in concentration over time. And so in order to avoid all of these different complications, we just deal with the reaction rate right as the reaction proceeds, or right as it starts. So now that we have this in mind, let's just look at this problem here. How exactly do we find the orders of, with respect to each of our reactants and write out this entire rate law. How do we find the rate constant? All of these things, we can figure out all of this from just this data that we have here and the general form of our equation and just a little bit of algebraic manipulation as always. So let's see exactly how we can do that. Well, what you're going to want to do first is pick 2 experiments. Or rather, let's do this. Let's first write out the general form. We know that that general form is your rate is equal to rate constant a to the m times b to the n. So how do we find this m and this n? Let's start off, let's try to find m first, right? The rate with order, the order of the reaction with respect to a. So what you're going to want to do is pick 2 experiments where the concentration of b is held constant, but a is changing. And then you are going to divide the rate equations, and doing so will cancel out your k as well as your b to the n terms, and you can solve for m. So let's do this here, and it'll make a lot more sense. So first, let's look at some experiments, a pair of experiments here, right, where b is constant and a is changing. Well, we can see here 0.1, 0.2, yeah. So if you look at experiments 1 and 2, we can see that we're holding the concentration of B the same. B is held at 0.1 molar, right? This M here is referring to molar, the concentration. Rate is in molarity per second. Again, it makes sense, right? So we're seeing that our reactant concentration of B is held at 0.1, but that of A is changing from 0.1 to 0.2. So this is perfect. We're also given the rates for experiment 2 and for experiment 1. So let's say we take the rate of experiment 2, rate of 2, divided by rate of 1. For this very first time, I'm going to write out all the terms just so it makes sense why we're doing this, right? So if we're writing out the rate of 2 over the rate of 1, we know that the rate constant, K, is the same for our reaction. So for the reaction A plus B yields products, that K is going to always be the same. So for writing out the rate law for reaction experiment 2, that's going to be K times, we're writing out the concentration of A is 0.2 to the m times 0.1, 0.1 to the n, right? And we can then divide by the rate law of 1. Which again, K is going to be the same. In this first one, we're going to have 0.1 to the m times 0.1 to the n. And what you'll notice is, and again, we're given the values of rate 2 and rate 1, so if we wanted to write that out, which we would later anyway, but that would just be 1 times 10 to the negative 2 divided by 2.5 times 10 to the negative 3. But in any case, what we'll see here is that since the concentration of B is held constant, when we write this out, well, firstly, we can cancel out the rate constant, because that's the same for both of these, and we can cancel out the 0.1 to the n term. And this leaves us with a very simple of expression, where we're simply dividing the concentrations of reactant A to the m, and we have our rate laws here. So if we kind of clean this up a little bit, we can see that if we do this, we simply get that is, we're simply going to get 0.2 to the m divided by 0.1 to the m, because everything else cancels out, and we know that this is going to be equal to the rates which were given, which is 1 times 10 to the negative 2 divided by 2.5 times 10 to the negative 3. Now, if we simplify this up a little bit, right, we can get rid of this. We know what they're talking about here. But simplifying this, 0.2 to the divided by 0.1, we know that to be, or actually first, let's do this in case you aren't, don't remember your exponent rules. You should know by now, again, with your exponent rules, that we have this expression, but we can simplify it. This is equivalent to writing 0.2 divided by 0.1, the whole thing raised to the m. So as long as you know this, you'll be fine. And then we can further simplify this, because we know that 0.2 divided by 0.1, that's simply 2. So 2 to the m is going to equal this fraction, which we and then simplify by dividing these two values. We're going to get an answer of 4. 4. And so our m is then going to be 2 raised to what power gives us 4? Well, we know that 2 squared is 4, so our m is going to be equal to 2. So this is the order of the reaction with respect to A. So let's keep this value over there, off to the side. M equals 2. Now let's do the exact same thing, but for B, right? We're going to try to find which experiments are we holding the concentrations of A constant and B is varying. So if you want to take a minute, do that yourself, set up the expression, try to figure out the value of N. All right, I'll assume you did that, and if not, let's work through this together, right? So once again, we're going to find the experiments this time with where we're holding the values of A constant, but B is changing. So we can see with experiments 1 and 3, A is held at 0.1, and B varies from 0.1 to 0.3. So what we're going to do here in this case, I'm not going to write it all out, but we can see that the rate of 3 divided by the rate of 1 is what we're going to want to do to set up this expression. So what is that going to be exactly? Well, let's see. The rate of 3. Again, remember the A's values are going to cancel out. So we only need to look at B this time. So that's just going to be 0.3 to the n divided by 0.1 to the n. And this is going to be equal to 2.25 times 10 to the negative 2 divided by 2.5 times 10 to the negative 3. Simplifying our values a little bit, well, firstly, we can simplify this expression, as you remember, to just be 0.3 divided by 0.1, this whole thing raised to the n. And again, actually doing some of our arithmetic here will give us our values. 0.3 divided by 0.1, well, that's 3 to the n. And our 2.25 times 10 to the negative 2, that whole thing, that expression is simply equal to 9. So what 3 raised to what power gives us 9? Well, that is going to be 2. 3 squared is 9. And so our value of n is going to be 2. So here, coincidentally, the orders of the reaction with respect to each of the reactants happens to be the same. This is not something that will always happen, so don't, be expecting that, or if you get a different value, don't think that you're wrong necessarily. So this is then going to be what we're given here. So what is the overall rate of the reaction? Well, the overall rate of the reaction is just going to be m plus n, or 2 plus 2, which is equal to 4. So this is a fourth order reaction overall. So now we know a bit more of information, right? If we want to write out the entire rate law, well, we know a little bit more information now. We know what our m and our n's are. So let's write that here. This is 2 and b to the 2. Now, what about when we want to find our k, our rate constant? How do we do that? Well, that should be very simple, right? We have a lot of information here. We already have the rates provided for us. We know the concentrations because those are also provided. And now we have the orders. So this is very much a plug and chug at this point. So just pick any experiment here that you want to and just use all the data there. So let's just start with let's just use the first experiment. So let's say we're given the rate here is 2.5 times 10 to the negative 3. We need to find k still, so let's write this k here. But we know A, its concentration is 0.1 molar, and we have the order is 2. Similarly, we can do the same thing for B. In this case, 0.1 to the 2. So now, all we have to do is our k is going to be, we can find it through a little bit of algebraic manipulation. Divide both sides by these values, and that's just 2.5 times 10 to the negative 3 divided by 0.1 squared divided by 0.1 squared. This is going to give us a k of 25. And this rate constant is actually going to have units as well. And these units are going to be varying based on the order of the reaction. Because this is an overall fourth order reaction, it's going to have the units of m to the negative 3 seconds to the negative 1. And depending on the order, again, this value is going to vary. Look out for a video where I explain how to figure out the units for different rates, different orders of reaction. But in any case, this here is then your rate constant. And so now we have all the information necessary to write out our rate law. So let's do that. So if we're told to find just the rate constant, you would do this. If you wanted just the rate law, I mean, just the orders or the overall order, you know how to do that now. But if you want to write out the overall rate law itself for this specific reaction, that's going to be rate equals, now we have our rate constant of 25 times A second times B to the second. So any concentrations of A and B that you plug in here, you're going to be able to figure out the rate given those constraints here. All right, so just a quick tip, or just the one thing really you need to keep in mind here is, this is again a very simple, straightforward type of problem, but you just need to make, as long as you're making sure that you're always picking experiments where only one reactant changes at a time. So in this case, we picked 1 and 3 because A is held constant at 0.1, and only B is changing. So that's the main thing to keep in mind. In any case, this again is the solution, the overall rate law for this problem. And so hopefully you found this helpful, you found some utility out of this video. If you did, please show your support by liking and subscribing, and leave any questions you may have in the comments or what you would like to see next. And I'll see you guys in the next video.